Now we'll dive into the quantitative and visual exploratory data analysis in Python portion of today's session. Exploratory data analysis is often referred to as EDA. Jupyter excels in this area, and there's a lot you can do. The purpose of this lesson is to give you a flavor for a data analysis workflow in a Jupyter notebook. You can take what you learn here and apply other tools within the libraries that we'll cover. Please note that it's better to do big jobs or heavy-duty computing outside of your local Jupyter environment because your system can get bogged down on bigger datasets. Hopefully you already have your Anaconda distribution installed or installing. If you do not, again, please go ahead and get that going now so you can join in on the analysis portion of the program today. If you're having trouble installing the software because of installation issues, i.e. you don't have admin rights to your computer, there are other ways to access Jupyter on your machine. First, you can try setting up an account using Microsoft's hosted Azure Notebooks. Second, if you'd rather not use the command line to open your Jupyter Notebook files, you can also install Interact, which was covered earlier in this training. Data science inherits much of its workflow from the scientific method. Data science is performed in several steps, not necessarily in this order. First, you pose a question or a problem. Second, you acquire data. Third, you explore the data, maybe by writing and running code. Fourth, you prepare and clean the data. Fifth, you complete an analysis and visualize the results. Sixth, you write up an analysis for publication and sharing, for example in blogs, journals, or on GitHub. And finally, you make an effort to reproduce other people's analyses. This process is much more iterative than linear. At every step, you may realize you need to go back and do something differently, even multiple times. It's common to run through all or parts of this process over and over again until meaningful results are obtained. There are lots of tools on the market for these steps, and Jupyter aims to package them into a single environment. Let's talk briefly about choosing an appropriate dataset for your first analysis. Since the purpose of this tutorial is to show you the general functionality of Jupyter and the Jupyter Notebook, I've chosen a dataset that is fairly clean and small enough to process quickly while I'm demonstrating tools in the ecosystem. Once you've built dexterity in Jupyter and the common data science libraries used in Jupyter, then go ahead and take on bigger and more complex datasets. If this is your first data analysis in the Jupyter Notebook, I recommend using the dataset used here in this tutorial or finding another dataset of interest that is manageable. Manageable meaning that the data is clean, easy for you to understand, and small enough to process quickly on your computer or in the Jupyter instance you have running on a shared server at work or at school. It's also important to pay attention to any licensing your dataset might have. The one we are using today does not have a usage or privacy agreement. The dataset we're using today was retrieved from data.gov, the home of the U.S. government's open data. Data.gov offers over 230,000 datasets for you to explore. To find a dataset, go to the website, data.gov, and either enter a search term for a topic you'd like to explore or click on Data for an advanced search of the data catalog. I'm going to click on Data to access the data catalog and scan the left panel that groups topics, categories, and formats that I may be interested in. Beware that there are many different formats available through data.gov, and some data sets are much more structured than others. So today, I'm looking for a CSV file, and it looks like over 18,000 CSV files are available. I'm curious about energy usage in 2010, and I type that into the search bar. Great. Look at that. There's a data set from the city of Chicago that we can explore. Please note that finding a good data set is not always this straightforward and can require some thought and research. Today I've done the legwork ahead of time so we can focus on our analysis. When I click on CSV, the CSV file is downloaded to my Downloads folder. I'll want to move it to the folder I'm working from to run my Jupyter Notebook. On a Mac, I can drag and drop it through the Finder window or use the command line. Once the file is moved to your working directory for this project, you're ready to move to the next video. Working with Python means a bounty of data manipulation and analysis tools is available at your fingertips. To use these tools, you must first import them into your analysis, using the conventions on this slide. Today, we'll use a handful of the most common Python libraries. There are hundreds more to choose from that you will encounter as you grow in your data science career. Several analogies that help illustrate the purpose of importing libraries include a chef setting out all the ingredients before preparing a dish, or a craftsperson setting out all her tools before starting in on a creative project. It's good to have some idea of the kind of analysis you plan to do before you start. Python libraries are pre-made collections of functions that allow you to do powerful work. Today we'll be using the libraries Pandas, NumPy, Matplotlib, and Seaborn, and we'll import them into our Jupyter Notebook using the conventions listed on this slide. scikit-learn, or sklearn for short, is a machine learning library that is frequently used in data science. Typically, you will import modules within sklearn rather than the entire library all at once using a slightly different convention. Libraries are imported by typing in the library name and then assigning a shorter name or an alias using as for easy access during coding. %sign matplotlib inline is the matplotlib inline operation, which invokes a IPython cell magic that instructs the visualization library matplotlib to show visualizations within the Jupyter Notebook instead of in a separate window. The first library we'll work with is Pandas. Pandas is the Python data analysis library created by Wes McKinney and is packaged with the Anaconda Python distribution we downloaded earlier. Pandas provides the ability to read in data, manipulate data, query data sources, and write data out of the Jupyter environment. Pandas allows you to interact with your data in a data frame, or a grid structure, similar to spreadsheet programs like Excel, Numbers, or Google Sheets, but through code rather than clicking with your mouse or using shortcut keys. We'll use Pandas to read our CSV file into our Jupyter Notebook. To import Pandas, go to your Jupyter Notebook and type the import statement, import Pandas as PD. Sometimes you might type improt and get an error, and that's okay. Fix it and try again. Maybe slow down a bit at first while you're developing mastery over the material. Great! Now with Pandas imported, you have its extensive data analysis tools available at your fingertips. First, let's read the energy data into our Jupyter Notebook as a Pandas data frame and assign the data frame to a variable df, which stands for data frame. We do this by typing df equals pd.read_csv, open parentheses, then the file name in quotes, and concluding it with a closing parenthesis. Note that if you save the CSV file to the same folder as your Jupyter Notebook, you do not need to specify a path. If your CSV file is stored in a different location than your notebook, you do need to specify the path. When typing your file name on a Mac, use forward slashes to separate the directories in your path and use backslashes on Windows. The name of your CSV file should be in double or single quotes. You can enter the file path directly into the read_CSV statement or save the file path to a variable named filename or something similar. If you don't recall the path to your file, you can interact with your file system through the Jupyter Notebook as if you were working from the command line by importing OS for operating system. After executing the import OS cell, you can navigate your file system with common Unix commands like ls, cd, makedir, etc. Also, to check which libraries you have installed, create a new code cell and type bang or exclamation point, which activates and runs shell commands, and conda list, which will generate a list of all the libraries installed and their versions. When you execute the pd.read_csv command by pressing Shift-Enter, you will not see any output. To see the imported data, you'll need to run additional commands. The first command we'll use to view our data is df.head, which outputs the first 5 rows of the data frame and provides you with an idea of the general structure and contents of your dataset. If your import worked, you should see the first 5 rows of your data frame with community area name as the first column. To see more rows, put the number of desired rows inside the parentheses of df.head. For example, df.head with 10 in the parentheses displays the first 10 rows. You can examine the last 5 rows by typing df.tail. If you choose to type df only, Pandas will print out the entire data frame. This may work fine with smaller data sets, but doing so with a large data set may overwhelm your system and grind your notebook to a halt. Another way to familiarize yourself with your data set is by finding the shape or the number of rows and columns of your data frame. Here I will apply the built-in function shape to the data frame df, which outputs the number of rows followed by the number of columns. This data frame is 67,051 rows and 73 columns. That's not a huge data frame, but more data than is needed for today's examples. We'll learn how to pare this down in a moment. When you just want to know the number of rows, you can apply the built-in length function, len, open close parentheses, to the data frame, len_df. Python will calculate the length of the data frame in number of rows, which in this case is 67,051 rows. Len can also be used to generate the number of columns by adding .columns to your len_df statement. len_df.columns returns 73 for 73 columns. What are these columns, you may ask? To find out, generate a list of all the column names by using the .columns attribute of the data frame by typing df.columns without parentheses. This is the same statement we put into the len function above. Another way to see the names of all the columns is by typing df.info parentheses. df.info will generate output of all the column names plus their data types and counts of the non-null cells in each column. We'll talk more about null values in a moment. But a word about data types. The data types available in Python are strings, integers, or ints, floats, and datetime. In pandas, strings are known as objects. In our df.info output, you see that pandas has listed not only the column names, but their data types, a mix of objects, ints, and floats. As I mentioned earlier, this dataset is larger than what is needed to illustrate the basic functionality of the Jupyter Notebook and the tools commonly used in Jupyter Notebook analyses. Since the dataset includes energy usage data for different types of buildings, we're going to pare down the dataset to a particular kind of building. First, let's see what the building categories are by using the .unique method on the building type column. We'll select building type using square brackets instead of dot notation because the column name building type has a space in it. Our output returns 3 building types: residential, commercial, industrial, and NaN, not a number. The NaN means some entries have a missing building type. Let's make our data frame smaller by selecting only the rows where building type equals the string object residential and saving that to df_res, res. Doing so will not only strip out the residential and commercial types, but also the rows where building type is NaN. In this statement, we're using the .loc command, which enables us to index by labels. I've also added several print statements to highlight the difference between the original data frame and the subsetted dataset. The output displays that the original dataset has been reduced by over 17,000 rows. The data frame still has 73 columns, most of which we won't use in our analysis. We can remove columns by selecting the columns we wish to keep using double brackets and saving that statement to our original variable name. The 8 columns we want to keep are listed here in the notebook, and we can save the subset to the original residential variable df_res. Running df_res.shape confirms that we now have 8 columns instead of 73 and nearly 50,000 rows. Now that we have a data set that we want to work with, it can be saved to our directory for safekeeping and also to share with others if we like. To save the subsetted data frame back to a CSV file, use df_res.to_csv, open parentheses, then enter the name of your new CSV file name in quotes within the parentheses, and close the parentheses. When you're ready to work with the data file again, you can load it from disk using the pd.read_csv command. On read, make sure to set the index column if there is an index. Usually column 0 is the index column. Now that we've loaded in our CSV file that contains the data for residential building types only, we'll want to make a working copy in order to keep the original subset pristine and intact. We'll start to manipulate and update the actual data in coming steps. So building off a working copy and having an original data set to go back to in case we make a mistake is critical. If we don't make a copy, any changes we make to the data frame will save, aka overwrite, our original data set. So let's save a copy of our imported dataset, df_res to df. Real-world data frequently contain missing information with either blank cells represented as nans, not a number, or with zeros, multiple nines, or other numbers in a row, strings like none, or some other indicator. How missing data is depicted in your data frame will affect how the analysis is conducted, what code you can run against your data, and even the statistical results of your data. Handling your missing values in a thoughtful way is imperative for a robust analysis. First, let's determine if we have missing values in our dataset. We know from running df.shape that there are 49,747 rows in our dataset. df.info displayed a list of column names and null value counts. Using the .count function also provides a count of all the non-null values for each column in your dataset without showing the data type. For this dataset, any columns that have counts less than 49,747 have null values. It looks like 4 of them contain null values. Let's use df.head to take a look at the data frame to see how the null values are represented. Sure enough, row 0 contains a nan under total kilowatt hours, kWh, as do 4 rows in the total therms column. We could replace the nans with zeros using df equals df.fillNA with 0.0 in parentheses, or with the mean for each column depending on how we want to execute our analysis. But let's keep the nans for now. You can also remove all rows that contain nans, but be careful. This move can wipe out a large portion of your dataset. Now that we're satisfied with how null values are represented in our dataset, we can perform basic statistics. The .describe method will output the count, mean, standard deviation, min, max, and quartiles for any given column. Let's do that now using total kilowatt hours by typing df, open square brackets, quote, total space kWh, close square brackets, .describe, open and close parentheses, and pressing Shift-Enter. The output displays the calculations I described: count, mean, standard deviation, min and max, and quartiles. Individual statistics on a column can also be retrieved. For example, standard deviation is generated using .std. .describe can also be applied to the entire data frame, executing down each column with a numeric type. Let's go ahead and type df.describe. Note that building subtype and community area name are not reported in the result because they are non-numeric columns. What if we run .describe on community subtype and community area name, our categorical columns? Pandas outputs a different data frame that again provides the count and also some very useful information like the number of unique values in each column, 3 building types, and 77 community areas, the top or most common category in each column, single family in Austin, and how many times or the frequency that the top category appears. Single family over 26,000 times, and Austin 1,974 times. Pretty neat, right? Now that we know how to generate basic statistics about our data, let's consider 3 targeted questions we can ask about the data. These questions are: 1. What was the average energy consumption for residential buildings broken down by building subtype in 2010? 2. What was the per capita energy consumption for all residential buildings? And 3. Which community areas were responsible for the highest and lowest per capita energy consumption in 2010? First, let's look at average energy consumption by building subtype. Let's take a moment to think about this question. Building subtype is a column in our data frame. The dataset contains data for 2010, so we don't need to perform any extra filtering there. To break our statistics down according to various groups, we can use the group by method. To elaborate, building subtype, in parentheses, is a parameter passed to the .groupBy method and specifies which column to group the results by. Total kilowatt hours, in brackets, further pares the result set down to only the values we are interested in, and .mean takes the average of those numbers, grouped by building subtype. In other words, this provides the mean of the total kilowatt hour readings in each category of building subtype. This output answers our question, what was the average energy consumption for residential buildings broken down by building subtype in 2010? Next, let's look at per capita energy consumption. The dataset provides consumption per building, but we can divide the total kilowatt hours column by the total population column to determine per capita consumption. Let's give that a shot. We'll start with the following statement and press Shift-Enter. Our output gives us inf for infinity, which is not what we expected. A result like this indicates a flaw in the data set and that we are performing a division by 0 or a nan somewhere, and that result bubbles up to our final mean calculation. To circumvent this, we can select only the rows that include valid values for both total kilowatt hours and total population. We'll do this by creating a copy of our original data frame and saving it to df_clean. We'll also use .loc to access data by column name, in this case total kilowatt hours, selecting all rows in the data frame where the total kilowatt hours is greater than 0 and where the total population is greater than 0. So then to find the average usage per person, we've again divided total kilowatt hours by the total population, but this time with zeros and ands filtered out. This output answers our question with the average being just over 1,559 kilowatt hours per person across all community areas. Finally, let's look at highest and lowest energy usage community areas per capita. To answer this question, we first calculate per capita energy usage as above, then group by area name, and then sort the list. We'll sort ascending, which is the default, so the first 5 results are the 5 lowest energy users per capita, and the last 5 are the highest. We'll take this one step at a time. Now let's look at the new column using .head. Now let's find the mean per capita kilowatt hours, grouped by area, and sorted by per capita kWh. First, let's create a new variable, df_area, to store our output in. In this case, group by provides groupings for all the unique community area names, and .mean takes the average of each numeric column for each group. Sort_values sorts the result set by per capita kilowatt hours in ascending order by default, showing the consumers with the lowest consumption at the top of the list and consumers with the highest consumption at the bottom of the list. And by typing df_area open square brackets per capita kilowatt hours .tail, we see that near Southside, Loop, Mount Greenwood, Forest Glen, and Beverly are the highest consumers per capita.